All right, we are now at Chapter 18, Chemical Thermodynamics. This is an expansion of the thermochemistry that we talked about last spring, or whenever you took the first semester. We're going to talk about the nature of spontaneity and introduce two new thermodynamic quantities, namely entropy and Gibbs free energy. So this is going to be broken up into three basic lessons. I have no idea how many actual videos it'll come out to. By the time we're done with this first lesson, you're going to demonstrate an understanding of entropy by making qualitative predictions of the sign of delta S for various processes and chemical reactions. You're going to be able to state the first, second, and third law of thermodynamics. There's a 0th law, but don't worry about that. It's pretty lame. Okay, spontaneity. What's it all about? So this is a question that chemists and physicists and people in general have been asking themselves for quite a while now. Is that why do some processes spontaneously occur in one direction and not the other? And typically in a Gen Chem class, these processes are often chemical reactions of some sort. And we have maybe led ourselves to believe that maybe the direction of spontaneous change is one where either energy or enthalpy is lower. Certainly that seems to work out that way quite a bit. But there are exceptions, and here is one of them. So here we've got ammonium nitrate. So this is a soluble salt, so if you remember your solubility rules. And it dissolves quite nicely in water. But this one does not actually result in a lowering in the enthalpy or energy of that particular system. This one happens to be spontaneous endothermic. This is how ice packs or some sorts of ice packs work. The kind that you kind of hit or snap and shake a bit. So the way those work is that there is an amount of ammonium nitrate in there. When you snap it, break it, hit it, whatever, you break open this container, it dissolves in the water, and the solution, the dissolution, actually requires energy to be taken in from the surroundings, the solution. So the solution that the ammonium nitrate is dissolved in actually gets cold, and you put it on your, sprained ankle or something. All right, so let's talk a little bit more about this whole lowering of energy thing. Now, one of the laws of thermodynamics that we did cover last semester was the first law, which says that the energy of the universe is conserved. So the idea of something going to a state of lower energy is a little tricky to talk about because, the energy of the entire universe isn't changing. So really, there often isn't a lowering in energy overall to consider. So that was a complication. Another complication is that spontaneity in many cases also depends on temperature. And lowering in energy, the energy or the enthalpy of a particular set of products or reactants doesn't really depend on temperature. It does a little itty bitty bit, but that's about it. And now to further complicate matters, I could propose to you a process where the energy of the system doesn't even change, much less the entire universe. And an example of such a process would be the expansion of helium gas into a vacuum. So here's the setup. I've got two glass bulbs. We'll say they're of equal size, connected by a valve. On one side, we have helium filled to 1 atmosphere, and on the other side, you've got nothing, a vacuum. Now, if I were to propose opening this valve here, I think all of you could guess exactly what's going to happen, that the helium would spontaneously flow from the 1 atmosphere side to the vacuum side and would continue to do so until there was a half atmosphere on both sides. The pressure would be equal, and as long as they were of the same volume, it would be half an atmosphere. Now, so this is important because helium is an ideal gas, and at moderate pressures, like 1 atmosphere or half an atmosphere, it really has no interactions with its neighbors. So if molecules get close, if the atoms are closer together or further apart from each other, it really doesn't matter because there aren't any distance-dependent interactions to begin with. So there is no energy change from simply having the gas take up a larger space. On top of that, in this particular process, no work is done because you're expanding against a vacuum, and that does not require work. So the system doesn't lose energy by expending work either, or by doing work, I should say. But clearly, so there's no change in energy, either from intermolecular forces or from the system doing work against something because there's a vacuum. But clearly, this process has a direction of spontaneity because what no one has ever observed is the reverse process, which would be taking a 2-bulb system with half an atmosphere of helium on both sides and having them spontaneously go to one side or the other. You know, I drew them all on the left side here, but they could just easily be all on the right side. That process never happens, so it happens in this direction, but never this one. So in this case, there is clearly no energetic change guiding the molecules to spread out. What is? So to further to explain this point, I'm going to simplify this system a little bit. From 1 atmosphere's worth of helium to simply 2 atoms of neon. And whether it's helium or neon, under these conditions, it doesn't matter. They're still, both of them are as ideal as the other. And so, but 2 of them represents a much more manageable system. You could even, label them atom A and atom B. And so the next question is, how can you distribute these? And basically the distribution parameters are going to be simply which ones are on the left side, if any, and which ones are on the right side, if any. And you could even have a little scheme where you draw them like this, where you label the atoms that are on the left side, a vertical bar, and then the atoms on the right. And you can probably figure out what these would look like. So here's an example of the first one. You have both of them on the left side of this container. Now, and also in this case, let's pretend this is open, and they can go wherever they want. And we would call this a B bar. And there are 3 other possibilities. Hit pause, think about them, and let's see if you got it. All right, welcome back. So the next one is simply put them both on the right side. And in our little language here, that would be called bar AB. The third one would be, let's say atom A is on the left side, atom B is on the right side, so we would call that one A bar B. And the fourth possibility is the reverse of this one. Atom B is on the left and atom A is on the right, and we would call that B bar A. Now, the important thing to understand is that all of these are equally probable. The motion of these atoms, so when we talked about the motion of gases last semester as well, that they are moving in random directions, and in this case they are not particularly coupled to each other. So the motion and position of neon atom A is completely independent of the motion and position of neon atom B. So, and being anywhere in this is probable is equally probable for both of these. So all of these configurations are equally probable. The question comes when could you actually tell them apart? In real life, neon atoms are quite small, and it is difficult to put labels on them, like A or B. So particularly these last two configurations, you couldn't tell them apart. So you have a 1 in 4 chance of observing at any instant in time a 1 in 4 shot of all of them being on the left. You also have a 1 in 4 chance of observing both of them being on the right. Now, but you can't tell between these two probabilities. So what you would say is that you have a 2 in 4 chance of observing a configuration where there is one on each side, where they're equally split up. So the distribution where they are evenly distributed throughout both bulbs is more probable. You are simply much, much more likely to see that. And that's actually it. The reason why that it seems to spontaneously go from this or this to one of these is simply because you have a greater chance of observing these two. Now, right now, this doesn't seem much. You're only twice as likely to see them one on each side as you are seeing them, all on the left or all on the right. And you would rightly think that if you looked at this long enough, or in this case, not very long at all, that you would observe at some point them all being on one side or all being on the other, and not just evenly split. And you're still more likely to observe this because there are more ways to achieve this particular configuration, where there's one on each side. The issue is that when you get to actual reasonable sample sizes, that this disparity between them all being on one side or the other and them being equally spread out is huge. So here's what it looked like, and even this is a ridiculously small sample size. It's 100 particles. And here, what I've got here is the number of configurations where, and how many on the x-axis is how many particles are on one side. So this here would state, this here at 0 would represent, let's say, them all being on the right side. And on the other end of the scale here, 100 would represent them all being on the left side. And here at 50 represents them being half on one side, half on the other. And just feast your eyes on this scale, which, so there is essentially one configuration where they are all on the one side. There is one configuration where they are all on the other side. There are 10 to the 29th configurations where there are 50 on one side and 50 on the other. And so nature tends to spontaneously move towards disordered states simply because they are more probable and those are the most likely that you are to observe. And if you are at all interested, here's the math. So for this system, the number of configurations is equal to the total number of particles factorial. That's what that exclamation point means. So, and what that means is multiplication of that number by every integer below it. So this would be for 100 factorial is 100 times 99 times 98 times 97 all the way down to 1. And then divided by the number on the one side factorial divided by the number on the other side factorial. And that's how you get, in many cases, there's just one way, one distribution gets them all on one side, one on the other, and 10 to the 29th of them where they are split up, where they're evenly distributed. Now note that, 49 and 51 on one side and the other are probable. In a real life sample, you don't notice plus or minus 1 or 2 atoms. So we're still talking, a huge number here, but it's probability, and that is all that it is. So in theory, this could happen. Now, if you think about it, there are probably a few dozen or maybe even 100 configurations of your laundry that you would consider to be folded and sorted. But there are billions and trillions of configurations of your clothes that you would consider to be not folded and sorted. And so you would probably have to do 10 to the 29th loads of laundry to observe this, but fingers crossed, it could actually happen.